There is a moon orbiting Mars right now that is closer to its planet than any other moon in the entire solar system. It circles Mars 3 times every single day, racing across the Martian sky so fast that it rises in the west and sets in the east. And every year it drifts 1.8 centimeters closer to the planet below. That sounds like nothing. But this has been happening for millions of years, and it will keep happening for millions more until Mars either rips it apart or pulls it down completely. The grooves carved across its surface may already be the first visible cracks of its destruction. Its name is Phobos. It means fear. And tonight, you will understand why. If you enjoy science that actually makes you think, hit like and subscribe. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. If you could stand on the surface of Mars on a clear night and look up, something would immediately feel wrong. You would see a moon, yes, but it would not behave the way a moon is supposed to behave. It would not drift slowly and gracefully across the sky the way our own moon does. It would move fast, visibly fast, crossing from one horizon to the other in roughly 4 hours. And it would travel in the wrong direction. On Mars, this moon rises in the west and sets in the east, reversing the motion of everything else in the Martian sky. You would watch it climb above the western horizon, race overhead, and disappear below the eastern edge of the world before the night was even halfway through. And then, a few hours later, you would see it again. Because this moon orbits Mars not once a day, not once every few days, but 3 times every single Martian day. It laps the planet. It outruns the rotation of the world it orbits. There is nothing else like it among the major moons of the solar system. Its name is Phobos. In Greek, the word means fear. It was named after the god of terror, the son of Ares, who rode into battle spreading panic among mortals. The name was given by the moon's discoverer, the American astronomer Asaph Hall, in 1877. But the real terror of Phobos has nothing to do with mythology. It has to do with what is happening to it right now. Slowly, invisibly, with a patience that only gravity can sustain. The story of how Phobos was found is itself a story about persistence in the face of almost certain failure. By the 1870s, no Martian moon had ever been observed. Multiple astronomers had searched during favorable oppositions, when Mars swung close to Earth and its vicinity could be examined under the best possible conditions. None had found anything. The consensus was quietly forming that Mars simply did not have moons, that the planet orbited alone, unaccompanied. Asaph Hall disagreed, or at least he wasn't ready to accept the conclusion without one more attempt. Hall was the senior astronomer at the United States Naval Observatory in Washington, and he had access to the observatory's Great Refractor, one of the most powerful telescopes in the world. The opposition of 1877 was going to be an exceptionally close one, with Mars approaching Earth to a distance that would not be matched again for years. If Martian moons existed, this was the time to find them. The problem was the glare. Mars is bright. Any small moon orbiting close to the planet would be overwhelmed by the reflected light of Mars itself, lost in the diffuse halo of scattered light that surrounded the planet's disk in even the finest telescopes. Hall devised a strategy to deal with this. He positioned the bright disk of Mars just outside the field of view of his eyepiece, blocking the worst of the glare while keeping the region of space immediately surrounding the planet visible. It was a painstaking technique. It required steady tracking, clear skies, and enormous patience, Night after night in early August of 1877, Hall searched. Night after night, he found nothing. The work was exhausting and discouraging. The telescope was manually operated, requiring constant adjustment to track Mars as it moved across the sky. The Washington summer was humid, and the atmospheric seeing was often poor, blurring the images and making faint objects impossible to detect. After more than a week of failed attempts, Hall was ready to give up. His wife, Angeline Stickney Hall, persuaded him to continue. Angeline was not merely a supportive spouse. She had studied mathematics at a time when very few women had access to advanced coursework, and she understood the significance of the search and the rarity of the observing opportunity. According to the account that has been passed down through astronomical history, she urged him to try for one more night. On the night of August 12th, 1877, Hall spotted a faint object near Mars. It was tiny, barely visible, hovering at the edge of detectability. Before he could confirm what it was, clouds rolled in and the observation was lost. He had to wait. For several nights, Washington weather refused to cooperate. Clouds, humidity, and poor seeing prevented useful observations. Then, on the night of August 16th, the skies cleared. Hall returned to the telescope, relocated the faint object, and confirmed that it was moving with Mars against the background stars. It was real. It was a moon. 2 nights later, on August 18th, he found a second object orbiting even closer to the planet. Within 6 days, he had discovered both moons. The announcement electrified the astronomical world. Mars had companions after all, but they were unlike anything anyone had expected. They were tiny, far smaller than any previously known moon. They were close, orbiting so near to Mars that they had been hidden in its glare for centuries. And one of them, the inner moon, moved across the sky in a way that seemed almost impossible, completing its orbit faster than the planet rotated below. Hall gave the outer moon the name Deimos, dread, and the inner moon kept the name by which history would remember it. He chose words that suited objects found hiding in the glare of a planet named For War. 2 small dark bodies that had evaded every telescope pointed in their direction for centuries. Decades later, the largest crater on Phobos was named Stickney, in honor of Angeline Stickney Hall. It was a quiet acknowledgement that the discovery might never have happened without her insistence on one more night. The crater that bears her name is the single largest feature on the moon's surface, a scar so dominant that it defines the geography of an entire hemisphere. Something is fitting about that. The woman who kept the search alive is memorialized by the most violent event in the recorded history of the world she helped reveal. Hall could not have known what he had found. He saw 2 faint points of light moving near a bright planet. He recorded their positions, calculated their orbits, and reported the results. The idea that one of those points of light was not merely orbiting Mars, but slowly falling toward it, locked into a trajectory that would end in destruction millions of years in the future, was beyond the science of his era. He discovered Phobos. Understanding what Phobos actually is would take another century and a half of observation, spacecraft visits, and computational modeling. But the seed was planted on that August night in Washington. A small, dark, misshapen world entered the catalogue of known objects in the solar system. And the clock that had been ticking since long before any human looked through any telescope continued to tick, indifferent to discovery, indifferent to naming, indifferent to the slow accumulation of knowledge. That would eventually reveal what the ticking meant, but confirming the decay with modern precision required instruments that no 19th century astronomer could have imagined. It required a spacecraft orbiting Mars itself, measuring the position of Phobos not from hundreds of millions of kilometers away through the shimmer of Earth's atmosphere, but from close range, with radio tracking systems capable of resolving distances to within meters. Before we get to that, we need to understand what Phobos actually is. Because even by the standards of a solar system full of strange worlds, this moon is an oddity. Phobos is small, extremely small. Its longest dimension is roughly 27 kilometers. Its shortest is about 18. If you placed it on top of a major city, it would not cover it entirely. It is not round. It is not even close to round. Its shape has been compared to a lumpy potato, a battered rock, a piece of cosmic rubble that somehow ended up trapped in orbit around a planet. And that description is not far from the truth. The surface of Phobos is dark. It reflects only about 7% of the light that hits it, making it one of the least reflective objects in the entire solar system. If you stood on it, the ground beneath your feet would appear nearly black. Fine dust and loose gravel stretching to a closed horizon in every direction. The gravity would be almost non-existent. You weigh roughly 1/1800th of what you weigh on Earth. A casual step could launch you off the surface entirely. A strong throw could send a rock into orbit around the moon, or even out of its gravitational reach altogether. The surface itself is battered. Craters cover almost every visible stretch of terrain, scars from billions of years of bombardment by meteoroids and micrometeoroids in the Martian environment. But one crater dominates everything. Stickney, named after Angeline Stickney Hall, the wife of the moon's discoverer, is a massive impact basin roughly 9 kilometers across. That is nearly a third of the entire length of Phobos. Whatever struck the moon to create that crater came terrifyingly close to shattering it entirely. Radiating outward from Stickney are fracture lines and grooves that stretch across the body like cracks in an eggshell. Visible evidence that the impact shook Phobos to its core. And then there are the other grooves, hundreds of them, long, shallow, parallel depressions carved across the surface in patterns that do not radiate from any single impact. Some stretch for kilometers, some are hundreds of meters wide. They cross over craters. They wrap around the moon's curved surface. They follow patterns that, when mapped carefully, align not with any impact event, but with something else entirely. Something internal. Something ongoing. Those grooves are one of the most important clues in this entire story. They are one of the most important clues in this entire story. But for now, register this. The surface of Phobos looks like something that is being slowly pulled apart. Here is what makes the orbit truly extraordinary. Phobos circles Mars at an average distance of roughly 9,376 kilometers from the planet's center. That means the gap between the surface of Mars and the surface of Phobos is only about 6,000 kilometers. To put that in perspective, our moon orbits Earth at an average distance of roughly 384,000 kilometers. Phobos is more than 60 times closer to Mars than our moon is to Earth. If you scaled Mars down to the size of a basketball, Phobos would be hovering less than 2 centimeters above the surface. No other known moon in the solar system orbits this close to its planet relative to the planet's size. Phobos is not just close, it is dangerously, abnormally, almost recklessly close. And because it is so close, it moves fast, Orbital mechanics dictates that the closer an object is to the body it orbits, the faster it must travel to maintain its orbit. Phobos completes one full orbit in 7 hours and 39 minutes. A Martian day, called a sol, lasts roughly 24 hours and 37 minutes. That means Phobos orbits Mars more than 3 times for every single rotation of the planet below. It is outrunning the ground beneath it. If you were standing on the Martian equator watching, Phobos would appear to move backward across the sky compared to the stars, the sun, and everything else, west to east, against the flow. This creates a situation that is unique in our solar system among significant moons. Phobos orbits below what is called the synchronous orbital altitude. This is the altitude at which a moon's orbital period exactly matches the rotation period of the planet it orbits. For Earth, that altitude defines geostationary orbit, the ring where communication satellites hover over a single spot on the surface. For Mars, the synchronous altitude sits at roughly 20,400 kilometers from the planet's center. Phobos is well below that line. It is orbiting at less than half the synchronous distance, and that single fact, that Phobos sits below the synchronous orbit of Mars, is the key to everything that follows. Compare this to what we are used to. Earth's moon orbits far above the synchronous altitude. Our moon moves more slowly than the Earth rotates beneath it. This means the tidal interaction between the two pushes the moon outward, away from us, at a rate of roughly 3.8 centimeters per year. Our moon is escaping. Slowly, imperceptibly, over billions of years, it is drifting farther from Earth. Every year, the distance between us grows by a hair's breadth. Phobos is doing the opposite, and the consequences of that opposition are irreversible. But before we reach the mechanics of what is pulling Phobos down, another mystery has puzzled scientists for decades. A mystery that goes back to the most basic question you can ask about any moon. Where did it come from? The origin of Phobos is one of the longest running unsolved problems in planetary science. 2 competing hypotheses have dominated the debate for more than 40 years, and neither one has been definitively proven. The first hypothesis is capture. In this scenario, Phobos was originally an asteroid, likely from the outer regions of the asteroid belt between Mars and Jupiter, or possibly from even further out in the solar system. At some point in the distant past, this small body wandered too close to Mars, was caught by the planet's gravity, and became trapped in orbit. This idea has the advantage of simplicity. Asteroids are common. Mars sits near the asteroid belt. The spectral characteristics of Phobos, its dark surface, its low reflectivity, and its apparent similarity to a class of primitive carbon-rich meteorites called carbonaceous chondrites, all loosely match what you would expect from a captured outer solar system body. But capture has a serious problem. Catching an asteroid into a stable, circular, near-equatorial orbit is extraordinarily difficult. An object approaching Mars on a random trajectory would typically either fly past the planet or crash into it. For it to be captured into orbit, something has to slow it down at exactly the right moment. Atmospheric drag could do this if Mars once had a much thicker atmosphere, but the math is tight. Gravitational perturbation from a third body could help, but the probabilities are low. And even if capture occurred, the resulting orbit would likely be highly elliptical and inclined, not the nearly circular equatorial orbit that Phobos occupies today. Getting from a wild captured orbit to the current one requires additional mechanisms of orbital evolution over very long time periods. and the details of that evolution remain unclear. The second hypothesis is formation from debris. In this scenario, a massive object struck Mars early in the planet's history, blasting enormous quantities of material into orbit around the planet. That debris formed a disk, and from that disk, one or more moons accreted. This is the same basic process believed to have formed Earth's moon after the giant impact with the protoplanet Theia roughly 4.5 billion years ago. The giant impact model for Phobos has gained significant traction in recent years. It elegantly explains the circular equatorial orbits of both Phobos and Deimos, Mars's other moons. Two randomly captured asteroids should not both end up in such well-behaved orbits. But two moons born from a single debris disk naturally would. Computer simulations have shown that a sufficiently large impact on early Mars could produce a debris disk massive enough to form moons in the right orbital range. The inner edge of the disk would produce material that eventually accreted into a body near or inside the synchronous orbit, while the outer edge would produce a smaller, more distant body. That inner body would be Phobos. The outer body would be Deimos. Deimos deserves a moment here, because it provides the sharpest contrast to Phobos, and helps illuminate what makes Phobos so unusual. Deimos is smaller, roughly 12 kilometers across, and it orbits much further from Mars, at a distance of about 23,460 kilometers from the planet's center. Crucially, Deimos orbits above the synchronous altitude. Its orbital period is roughly 30 hours, several hours longer than a Martian day. This means the tidal interaction between Deimos and Mars is pushing Deimos outward, away from the planet, in the same direction our moon is moving relative to Earth. Deimos is slowly escaping. It is the safe sibling, the moon that got the lucky orbit, the one moving in the direction of freedom. Phobos got the other orbit, the one below the line, the one that leads down. There is a third possibility for Phobos' origin that sits somewhere between the two main hypotheses. Some researchers have proposed that Phobos is not a first-generation moon at all, but a recycled one. In this scenario, an earlier, larger moon of Mars formed from impact debris billions of years ago, spiraled inward due to the same tidal forces acting on Phobos today, and was eventually torn apart when it crossed a critical distance from the planet. The debris from that destruction formed a ring around Mars. Over time, material from that ring reaccreted into a new, smaller moon, which began its own inward spiral. This cycle of moon formation, tidal decay, destruction, ring formation, and reaccretion may have repeated several times over the history of Mars. If this model is correct, the Phobos we see today is not the original. It is the latest in a line of doomed moons, each one smaller than the last, each one born from the wreckage of its predecessor. The current Phobos would be the final generation, or close to it. A small, battered remnant of a process that has been grinding moons down for billions of years. This idea, proposed by researchers Andrew Hesselbrock and David Minton in a study published in Nature Geoscience in 2017, has profound implications. It means Mars may have had a visible ring at multiple points in its history. It means the surface of Mars may be littered with material that once belonged to earlier moons, rained down over geological time as rings decayed. And it means Phobos is not simply a moon in decline. It may be a moon that was born from decline. A moon whose very existence is a product of the same destructive cycle that will eventually destroy it. The Japan Aerospace Exploration Agency JAXA is preparing to send a spacecraft to Phobos that may settle the origin debate once and for all. The mission is called MEMX, which stands for Martian Moons Exploration. It is scheduled to launch later this year in 2026. The spacecraft will enter orbit around Mars, conduct extensive remote observations of both Phobos and Deimos, and then do something no mission has ever done before. It will land on Phobos. It will collect at least 10 grams of surface material using 2 different sampling systems. And it will bring those samples back to Earth, with arrival expected in 2031. Those 10 grams of dust and rock may contain the answer. If the samples show compositions consistent with primitive asteroid material from the outer solar system, capture becomes the leading explanation. If they show signatures of Martian crustal material, mixed and processed by a giant impact, the debris disk model wins. And if the samples reveal evidence of multiple generations of processing, of material that has been accreted, destroyed, and reaccreted, it could support the recycling hypothesis. Phobos is holding its origin story in the dust on its surface. And for the first time in history, we are going to go pick it up. But regardless of how Phobos got there, the situation it is in right now is the same. And the situation is not good. Let us return to the orbit. 6,000 kilometers above Mars. 7 hours and 39 minutes per revolution. Below the synchronous line. Moving faster than the planet rotates. Every one of those facts is a measurable, confirmed, repeatedly verified observation. Spacecraft have been tracking Phobos' orbit for decades. The Mars Global Surveyor, Mars Express, and the Mars Reconnaissance Orbiter have all contributed precise measurements of its position, speed, and altitude over time. And those measurements show something that does not require interpretation or modeling to understand. It requires only arithmetic. Phobos is getting closer to Mars, not occasionally, not randomly, consistently. Every year, every orbit, every revolution, the distance between Phobos and Mars shrinks by a tiny but measurable amount. The current best estimate, derived from spacecraft tracking data analysed over multiple decades, is approximately 1.8 centimeters per year. Some measurements frame it as roughly 1.8 meters per century. Either way, the direction is the same: inward, downward, closer. 1.8 centimeters per year is invisible on any human timescale. You could watch Phobos orbit Mars for your entire life and never notice the difference. A century from now, it will be roughly 1.8 meters closer. 1,000 years from now, roughly 18 meters. These numbers feel meaningless against the backdrop of a 6,000 kilometer gap. But the solar system does not operate on human timescales. It operates on timescales where 1.8 centimeters per year becomes a death sentence. 1 million years from now, Phobos will be roughly 18 kilometers closer to Mars. 10 million years from now, roughly 180 kilometers closer. And somewhere in the range of 30 to 50 million years from now, depending on the models, depending on assumptions about the internal structure and strength of the moon, Phobos will cross a boundary from which there is no return. Scientists call it the Roche limit. It is the distance at which the tidal forces from Mars will exceed the gravitational forces holding Phobos together. When that happens, the moon will be pulled apart, not by a collision, not by an explosion, not by any sudden catastrophic event, by the quiet, patient, relentless pull of gravity working on a body that has been getting weaker and closer for longer than human civilization has existed. longer than our species has existed, longer than most of the species that have ever lived on Earth have existed. The process is already underway. It has been underway for millions of years. The grooves on the surface of Phobos, the ones that do not radiate from any impact crater, the ones that follow strange parallel patterns across the body's face, may already be the first visible evidence of a moon being torn apart from the inside. And here is what no one tells you when they first describe Phobos as a small, strange moon of Mars. Every single orbit, every single revolution that takes 7 hours and 39 minutes to complete, brings it fractionally closer to the planet below. Every 7 hours and 39 minutes, Phobos completes another revolution. Every revolution tightens the spiral by a fraction too small to measure with anything but the most precise instruments. And every revolution brings the moon a little closer to the thing that will eventually destroy it. Phobos does not know it is doomed. It has no awareness, no capacity for fear despite its name. But the physics knows. The math knows. The measurements confirm it. And the surface of the moon itself, scarred and grooved and fractured, is recording the evidence in real time. The fall has already begun. The question is not whether Phobos will be destroyed. The question is what that destruction will look like when it comes. And to answer that, we need to understand the force that is doing the pulling. A force so fundamental, so ancient and so patient that it has been reshaping moons and planets since the solar system was young. A force that most people think of as simple attraction, but that operates on orbiting bodies with a subtlety and a cruelty that only becomes clear when you see what it does over millions of years. That force is tidal interaction. And what it is doing to Phobos is one of the slowest acts of destruction in the known universe. To understand what is killing Phobos, you first need to understand what a tide actually is. Not the version you learned about in school, where the moon pulls on the ocean and the water rises. That is the effect. The cause runs deeper, and it is the cause that matters here. Gravity is not a single uniform pull. It is a gradient. The strength of gravity depends on distance. The closer you are to a massive object, the stronger the pull. The farther you are, the weaker it becomes. This is not a subtle effect. It follows an inverse square law, meaning that doubling the distance reduces the gravitational force to 1/4 of its original strength. This relationship governs everything in orbital mechanics, and it is the engine behind tidal forces. When a moon orbits a planet, the side of the moon closest to the planet experiences a stronger gravitational pull than the side farthest away. The difference between those two pulls is the tidal force. It stretches the moon along the line connecting it to the planet, compressing it slightly in the perpendicular directions. The result is that any orbiting body, no matter how rigid, is being gently squeezed and elongated by the gravity of the object it circles. But the effect works both ways. The moon also raises tides on the planet. Just as the moon raises tidal bulges in Earth's oceans, Phobos raises tidal bulges on Mars. Not in water. Mars has no oceans. The bulges occur in the solid body of the planet itself. Rock is not perfectly rigid. Under sustained gravitational stress, even solid planetary mantles deform slightly, flexing by tiny amounts in response to the gravitational tug of an orbiting body. These are called body tides, and they are real, measurable, and profoundly important. Now here is where the geometry becomes lethal. If a moon orbits at exactly the synchronous altitude, it moves at exactly the same rate as the planet rotates beneath it. The tidal bulge the moon raises on the planet sits directly below the moon at all times. The gravitational interaction between the bulge and the moon is perfectly aligned. No energy is lost, no orbit changes. The system is in equilibrium. But Phobos does not orbit at the synchronous altitude. It orbits far below it. It moves faster than Mars rotates, and this changes everything. Because Phobos races ahead of Mars's rotation, it also races ahead of the tidal bulge it raises on the planet. Mars is a physical body. It is not infinitely responsive. When Phobos tugs on the Martian interior, the rock does not deform instantaneously. There is a lag. The material takes time to respond, to flex, to reach its maximum deformation. By the time the bulge fully forms, Phobos has already moved ahead in its orbit. The bulge is left trailing behind, slightly offset from the line connecting the centers of Mars and Phobos. That offset is where the destruction lives. The tidal bulge is a concentration of mass. It has its own gravitational pull, and because it sits slightly behind Phobos, its gravitational pull acts on the moon from behind, like a hand reaching back and tugging on a runner's shirt. The force is tiny. On any given orbit, it is almost immeasurably small, but it is always there. Every single orbit, the trailing bulge pulls backward on Phobos, stealing a fraction of its orbital energy. When an orbiting object loses energy, it does not slow down in the intuitive sense. It drops to a lower orbit. And at a lower orbit, it actually moves faster because orbital speed increases as altitude decreases. This is one of the counterintuitive truths of orbital mechanics that makes tidal decay so relentless. Phobos loses energy. It drops lower. It speeds up. It gets further ahead of the tidal bulge. The offset increases. The backward pull gets slightly stronger. It loses more energy. It drops lower still. The process feeds itself. It is a one-way ratchet. And there is no mechanism in the Mars-Phobos system that can reverse it. Compare this to what happens with Earth's moon. Our moon orbits above the synchronous altitude. It moves more slowly than Earth rotates beneath it. The tidal bulge that the moon raises on Earth is carried ahead of the moon by Earth's rotation, because Earth spins faster than the moon orbits. The bulge leads the moon instead of trailing it. The gravitational pull of that leading bulge acts on the moon from ahead, like a hand pulling a runner forward. It adds energy to the moon's orbit. The moon climbs to a higher orbit. It moves farther from Earth. It drifts outward at roughly 3.8 centimeters per year. The same physics, the same mechanism, the same tidal interaction. But because our moon is above the synchronous line and Phobos is below it, the outcomes are opposite. Earth's moon gains energy and retreats. Phobos loses energy and falls. One is escaping. The other is being consumed. This is not a theory awaiting confirmation. The orbital decay of Phobos is one of the most precisely measured phenomena in planetary science, and the story of how it was first detected is one of the stranger chapters in the history of the space age. In 1945, the American naval astronomer B.P. Sharpless published a study of Phobos's orbital motion based on observations stretching back to the moon's discovery in 1877. He was comparing the predicted positions of Phobos against the positions actually recorded at telescopes across nearly 7 decades of observation. The data showed something unexpected. Phobos was consistently arriving at its predicted positions slightly ahead of schedule. The discrepancy was tiny but persistent, and it pointed in one direction. The moon's orbital period was getting shorter. A shorter orbital period meant a lower orbit. A lower orbit meant the moon was moving inward. Sharpless reported this finding, and for a time, the community noted it and moved on. The effect was small, the data sparse, and the implications not immediately alarming. But roughly a decade later, the observation attracted the attention of a Soviet astrophysicist named Iosif Shklovsky, and his interpretation of it became one of the most famous wrong ideas in the history of space science. Shklovsky was a brilliant and creative thinker, well regarded for his contributions to astrophysics and radio astronomy. In 1959, he published a paper arguing that the rate of Phobos's orbital decay was too fast to be explained by tidal forces alone. He proposed that the only way to account for the observed acceleration was if Phobos were experiencing significant atmospheric drag from Mars's upper atmosphere. And the only way atmospheric drag could produce the observed effect on a body that size would be if Phobos were extraordinarily light for its dimensions. Shklovsky's conclusion was startling. He suggested that Phobos might be hollow. He did not explicitly claim it was an artificial structure, but the implication was difficult to miss. And in the context of the late 1950s, at the height of both the space race and public fascination with extraterrestrial life, the idea generated enormous attention. It was wrong. The orbital data Shklovsky relied on contained errors that exaggerated the decay rate. When better observations became available in the 1960s and 70s, the measured decay rate was lower than Shklovsky had calculated, and it was entirely consistent with tidal dissipation within Mars. There was no need for atmospheric drag. There was no need for a hollow interior. Phobos was exactly what it appeared to be. A small, dense, natural body spiraling inward because of tidal forces. The hollow moon hypothesis evaporated. But the episode served a purpose. It drew attention to the orbital decay of Phobos at a time when planetary science was still in its infancy. It forced researchers to quantify the tidal dissipation rate inside Mars, to build models of the planet's interior that could explain the observed rate, and to take seriously the idea that Phobos's orbit was not stable. The wrong answer led to the right question, and the right question, what is pulling Phobos inward and how fast, has been central to Martian science ever since. The Mars Global Surveyor, which orbited Mars from 1997 to 2006, provided detailed altimetric data that refined the decay rate. The European Space Agency's Mars Express, which has been orbiting Mars since 2003, conducted multiple close flybys of Phobos, some passing within 50 kilometers of the surface, and used Doppler tracking to measure the moon's orbits with extraordinary precision. The data from these missions converged on a consistent figure. Phobos is approaching Mars at a rate of approximately 1.8 centimeters per year. Some sources express this as roughly 1.8 meters per century. The numbers are consistent. The direction is unambiguous. Inward. That rate also tells scientists something important about Mars itself. The speed of tidal decay depends on how efficiently the planet dissipates tidal energy internally. A planet that deforms easily and dissipates energy quickly will produce a faster decay. A planet that is more rigid and dissipates energy slowly will produce a slower decay. By measuring how fast Phobos is falling, researchers can work backward to estimate the tidal dissipation rate inside Mars, which in turn constrains models of the planet's interior structure. Phobos's orbit is not just a doomed trajectory, it is a probe, an instrument that reveals the hidden mechanical properties of the planet it circles. Every centimeter of descent carries information about the viscosity, temperature, and composition of the Martian mantle thousands of kilometers below. There is a deeper layer to this energy exchange that most descriptions leave out. When the trailing tidal bulge pulls backward on Phobos and steals orbital energy, that energy does not simply vanish. Energy is conserved. It has to go somewhere. And where it goes is into the interior of Mars itself. The tidal bulge is a deformation. Mars's mantle is being flexed, pushed outward toward Phobos, and then allowed to relax as Phobos moves on. This flexing is not perfectly elastic. The Martian interior is not a spring that stores and returns all the energy of deformation without loss. Some fraction of the energy is dissipated as heat through internal friction within the mantle rock. Every orbit, Phobos transfers a tiny amount of its orbital energy into thermal energy inside Mars. The planet warms imperceptibly from the friction of its own tidal response to the moon above. This is the same process that heats other tidally stressed bodies in the solar system. Jupiter's moon Io is the most extreme example. The tidal forces from Jupiter, amplified by orbital resonances with Europa and Ganymede, flex Io so violently that its interior is partially molten, driving hundreds of active volcanoes across its surface. The energy powering that volcanism comes from the same fundamental process as the energy draining Phobos' orbit: tidal dissipation. The difference is one of scale and configuration. Io's tidal heating is enormous and expressed as surface volcanism. Mars's tidal heating from Phobos is minuscule and expressed only as a faint thermal signature buried deep in the mantle. But even that minuscule heating carries information. The rate at which Mars dissipates tidal energy depends on the viscosity, temperature, and composition of its mantle. A warm, partially molten mantle dissipates energy quickly. A cold, rigid mantle dissipates it slowly. By measuring the orbital decay rate of Phobos with high precision, scientists can work backward to constrain the dissipation factor of Mars, a quantity that reveals the planet's internal mechanical state in ways that no other measurement can. This is why the Mars Express mission's close flybys of Phobos were so scientifically valuable beyond simply photographing the moon. The Doppler tracking data from those flybys allowed researchers to refine the orbital decay rate, and through it, to probe the hidden viscosity of the Martian mantle from above. Phobos is dying. And as it dies, its death carries a signal that tells us what the inside of Mars is made of. The falling moon is an instrument. Its destruction is a measurement. Now consider how that rate translates across different timescales, because the numbers deserve to be felt, not just stated. 1.8 centimeters per year. In the span of a single human lifetime, roughly 80 years, Phobos moves approximately 1.4 meters closer to Mars. You could measure the total inward drift of an entire human life with a tape measure stretched between your outstretched hands. In the roughly 10,000 years since the beginning of human civilization, since the first permanent settlements and the first written records, Phobos has moved roughly 180 meters closer to Mars. The entire history of cities, empires, languages, and written thought corresponds to a distance you could walk in under 2 minutes. In the 66 million years since the asteroid impact that ended the age of the dinosaurs, Phobos has moved substantially closer to Mars, even accounting for the fact that the decay rate was slower when the orbit was wider. The accumulated drift over that span represents a significant fraction of the remaining gap. The moon that hung above Mars when the last dinosaurs were alive on Earth was noticeably higher in the Martian sky than the one that orbits there today. Over truly deep time, the picture becomes harder to calculate precisely, because the decay rate is not constant. When Phobos was farther from Mars, the tidal forces were weaker and the inward drift was slower. The current rate of 1.8 centimeters per year reflects the moon's present proximity. Millions of years ago, when the orbit was wider, the rate was gentler. This means a simple backward projection overstates how far the moon has traveled, but the direction is certain. At the time of the Cambrian explosion, roughly 540 million years ago, when the first complex animal life appeared in Earth's oceans, Phobos was orbiting substantially higher than it does today. It was a different moon in a different sky. Higher, slower, safer. The tidal mechanism was already operating, already stealing energy, already pulling the moon inward. It was simply doing so more slowly, because the grip of Mars was not yet as tight. The numbers do not shout, they do not need to. Laid end-to-end across geological time, 1.8 centimeters per year becomes a distance that dwarfs mountains. Now, let us talk about what waits at the bottom of this descent. Because Phobos is not falling toward a collision in the simple sense. It is falling toward a boundary, a threshold defined by the balance between two forces. One is the self-gravity of the moon, the force that holds its material together. The other is the tidal force from Mars, the differential pull that tries to tear it apart. As Phobos moves closer to Mars, the tidal force grows stronger. At some critical distance, it will exceed the moon's ability to hold itself together. That distance is called the Roche limit, named after the French astronomer Edouard Roche, who first calculated it in 1848. The concept is elegant and terrifying in equal measure. Every planet has a Roche limit for every density of orbiting material. Cross inside that limit, and gravity alone cannot keep a body intact. The tidal gradient overwhelms cohesion. The object is pulled apart, not by a single dramatic force, but by the quiet arithmetic of differential gravity. The near side is pulled harder than the far side. The difference grows as the distance shrinks. Eventually, the difference wins. Here is the detail that makes the situation even more unsettling than it first appears. When you calculate the fluid Roche limit for a body with Phobos's density orbiting Mars, accounting for the density difference between the planet and the moon, the answer comes out to roughly 3.14 Mars radii from the planet's center. Phobos currently orbits at approximately 2.76 Mars radii. It is already inside the fluid Roche limit. If Phobos were a perfectly fluid body held together by nothing but its own gravity, it would already be breaking apart right now at its current altitude. The only reason it still exists as a coherent object is that it possesses some degree of internal strength beyond pure self-gravity, friction between its constituent blocks, compaction of surface regolith, and possibly some mineral bonding in its outer layers. These modest structural forces are the only things standing between Phobos and immediate disintegration. It is not approaching the danger zone, it is already in it. And every year, as the orbit shrinks and the tidal forces grow, the margin between the strength holding Phobos together and the forces trying to pull it apart gets narrower. The question is not whether Phobos will cross a sharp boundary and suddenly fall apart. The question is at what distance the tidal forces finally overwhelm whatever internal strength the moon possesses. If Phobos is essentially a rubble-pile, a loose collection of rocky fragments held together primarily by friction rather than material bonding, the remaining margin may be thinner than it appears. The disruption would begin gradually as stresses exceed friction limits, with surface material shifting, blocks separating, and the overall shape slowly distorting before the body loses coherence entirely. If Phobos has more internal cohesion, if its outer shell has a tensile strength of even a few kilopascals, it could survive somewhat longer, enduring to a closer distance before failing. But even modest cohesion only delays the inevitable. It does not prevent it. The tidal forces increase as the orbit shrinks, and at some point, any realistic level of internal strength will be exceeded. Recent numerical simulations have attempted to answer that question by modeling how a rubble-pile with Phobos' shape and estimated material properties would behave as tidal forces intensify. The results suggest that the actual disruption distance, the point where a body like Phobos begins to lose structural coherence, sits somewhere between the rigid and fluid Roche limits, in a range that depends sensitively on internal strength and shape. What those models reveal about how Phobos will come apart is as important as when. The timeline estimates for when Phobos will reach the Roche limit range from roughly 10 million to roughly 50 million years, depending on the model. Some researchers have calculated a figure closer to 30 million years. Others, using different assumptions about interior properties and tidal dissipation rates, arrive at closer to 50 million years. A planetary dynamics analysis placed the figure at approximately 10.4 million years. The variation reflects genuine scientific uncertainty about factors that are difficult to measure remotely, including Phobos' internal density distribution, porosity, material strength, and the precise tidal dissipation characteristics of the Martian interior. What none of these estimates disputes is the direction. Every model, every calculation, every data set agrees. Phobos is moving inward. The orbit is shrinking. The tidal forces are increasing. And at some point in the geologically near future, the moon will cross the threshold. To a human being, 30 million years sounds like forever. And in the context of a single life, it is. But in the context of the solar system, it is extraordinarily brief. Mars is roughly 4.5 billion years old. 30 million years is less than 1% of the planet's total history. If the entire lifespan of Mars were compressed into a single calendar year, Phobos' remaining time would amount to the last day or two of December. The clock is not starting. The clock is almost finished, and the decay is not linear. As Phobos moves closer to Mars, the tidal forces increase. The energy loss per orbit grows. The rate of descent, while currently approximately 1.8 centimeters per year, will accelerate as the moon gets closer and the tidal interaction intensifies. The final stages of the spiral will be dramatically faster than the current phase. Millions of years from now, the descent that currently takes a century to produce 1.8 meters of altitude change could be producing the same change in a fraction of that time. The spiral tightens. The pace quickens. The end approaches not at a steady walk, but at an accelerating run. There is another way to think about what is happening. Every orbit Phobos completes takes slightly less time than the one before. The orbital period is shrinking as the orbit shrinks. Right now, the change per orbit is so small that it would take years of precise measurement to detect it directly. But it accumulates. Over centuries, the accumulated shift becomes detectable in the timing of the moon's position against its predicted ephemeris. Over millennia, the shift becomes substantial. Over millions of years, the orbital period will have shortened dramatically, and the moon will be visibly closer to the planet for any hypothetical observer, watching with sufficient patience. This is what scientists mean when they say Phobos is falling. It is not falling in the way a rock falls from a cliff, straight down under the pull of gravity. It is falling in the orbital sense, spiraling inward along a path that gets tighter and lower with every revolution. Each orbit is a circle that is fractionally smaller than the one before. Each pass over the Martian surface brings Phobos fractionally closer to the ground below. The spiral is so gentle that it looks like a circle, but it is not a circle, it is a contracting spiral. And contracting spirals have endpoints. It is worth pausing to consider what this means in the broader context of the solar system. Tidal decay is not unique to Phobos. It is a universal process that affects any moon orbiting below the synchronous altitude of its planet. Several moons in the solar system are in this configuration. Triton, the largest moon of Neptune, orbits in a retrograde direction, which means the tidal interaction is pulling it inward regardless of its altitude. Triton, too, is spiraling toward eventual destruction, though on a much longer timescale due to its greater distance from Neptune and the different tidal dynamics of that system. But Phobos is the most dramatic active case. Its small size, its close orbit, its position deep inside the synchronous radius, and its likely weak internal structure all combine to make it the most visibly doomed moon we can study. It is a laboratory for understanding tidal destruction, and it is a preview of a process that will eventually claim other moons in other systems across the galaxy. The measurements are real, the physics is settled, the trajectory is confirmed. Phobos is losing the fight against Mars's gravity, and it has been losing that fight since long before any human being existed to notice. The decay was happening when the first primates appeared on Earth. It was happening when the dinosaurs went extinct. It was happening when the first complex life emerged in the oceans. Phobos has been falling for so long that its descent predates most of the life that has ever existed on our own planet. And yet, from the Martian surface, nothing looks wrong. Phobos crosses the sky 3 times a day, just as it has for millions of years. It rises in the west and sets in the east. It does not look like something that is falling. It does not behave like something in distress. It looks like a moon doing what moons do, orbiting a planet, steady and reliable and permanent. That appearance is a lie. The orbit is not steady. It is contracting. The altitude is not constant. It is decreasing. The future is not open. It is closing, slowly, centimeter by centimeters, orbit by orbit, year by year, millennium by millennium. The tidal bulge on Mars never stops trailing. The backward pull never relents. The energy drain never pauses. Not for a single orbit. Not for a single revolution. Not for one of the more than 40,000 orbits Phobos completes every decade. And if the orbit is the story of how Phobos will die, the surface is where the evidence is already written. Because the forces that are stealing Phobos's orbital energy are also doing something else. They are flexing the moon, stretching it, squeezing it, warping its shape with every orbit as the tidal gradient shifts across its irregular body. And that flexing, that constant mechanical stress applied to a small, porous, fragile object over millions of years is leaving marks. The grooves on Phobos are not old scars from a forgotten impact. Many of them may be fresh wounds from an ongoing process. They may be the visible signature of a moon being deformed by the same force that is pulling it inward. Stress fractures in the surface layer of a body that is being slowly, patiently, and irreversibly torn apart. Those grooves are the next piece of this puzzle. And what they reveal about the state of Phobos right now, not millions of years from now, but today, is among the most unsettling discoveries in modern planetary science. If you could fly over the surface of Phobos at low altitude and look down, you would see something that no other moon in the solar system shows with such disturbing clarity. Across almost every face of this small, dark, battered world, lines have been carved into the terrain. They are not random, they are not chaotic. They run in long, shallow, roughly parallel tracks that stretch for kilometers across the surface, cutting through ancient craters, crossing ridgelines, and wrapping around the curvature of the body as though drawn by an enormous hand, dragging its fingers through wet clay. There are hundreds of them. Some are narrow troughs barely 10 meters wide. Others are depressions stretching 200 meters or more across and 10 to 20 meters deep. Many run in closely spaced groups, separated by regular intervals, creating corrugated patterns that cover vast sections of the surface. From certain angles, Phobos looks less like a natural body and more like something that has been scored, etched, worked over by a process that is both systematic and relentless. These features are called grooves, and they have been one of the most debated features in planetary science since the Viking orbiters arrived at Mars in 1976 and returned the first close-up photographs. Scientists examining those images were immediately struck by the grooves. Nothing quite like them had been seen on any other small body. They were clearly not impact craters. They did not radiate from a single point the way ejecta patterns do. They were too regular, too parallel, too widespread to be the result of random bombardment. Something else had made them. The question was, what? The first and most intuitive explanation pointed to the Stickney crater. Stickney is enormous relative to Phobos, a 9-kilometer impact basin punched into a body only 27 kilometers long. The impact that created it must have been catastrophic, releasing enough energy to send shockwaves reverberating through the entire moon. Researchers propose that the grooves were fractures caused by this impact, cracks radiating outward through the surface material as the shockwave propagated across and through the body. This was a reasonable hypothesis. Large impacts on small bodies can produce global-scale fracturing. The pattern made geometric sense for some of the grooves nearest to Stickney, but the more carefully scientists map the grooves, the less well the Stickney explanation held up. Many grooves do not radiate from Stickney at all. Their orientations point in directions that have no geometric relationship to the crater. Some grooves appear to be younger than Stickney, cutting across features that post-date the impact. And the distribution of grooves across the surface follows a pattern that correlates not with any impact site, but with something else entirely. Something that has to do with the relationship between Phobos and Mars. The breakthrough came from a research team led by Terry Herford at NASA's Goddard Space Flight Center. In a study published in 2016, Herford and his colleagues proposed that the majority of Phobos's grooves are not impact fractures. They are tidal stress fractures. They are the visible signature of Mars's gravity pulling Phobos apart. The argument rests on a detailed calculation of the stress field acting on Phobos's surface. As the moon orbits Mars, tidal forces stretch it along the line connecting it to the planet and compress it in the perpendicular directions. Because Phobos is not a perfect sphere but an irregular, lumpy body, these stresses are not uniform. They vary across the surface, creating zones of tension and zones of compression that shift as the moon rotates and orbits. Herford's team computed the orientations of the maximum tensile stress at every point on the surface, and compared them to the observed orientations of the grooves. The correlation was striking. The vast majority of prominent grooves are oriented perpendicular to the direction of maximum tension, exactly where you would expect fractures to form if the surface were being pulled apart by tidal forces. The grooves are concentrated symmetrically around the sub-Mars point, the spot on Phobos that always faces Mars, and the anti-Mars point on the opposite side. These are precisely the locations where tidal stretching is strongest. The pattern does not match Stickney, it matches Mars. For this model to work, Phobos needs a specific kind of internal structure. The deep interior must be weak. If Phobos were a solid, rigid block of rock, the tidal stresses at its current orbital distance would not be strong enough to fracture the surface. The forces are too small to crack a monolithic body. But if the interior is essentially a rubble pile, a loose aggregate of rocky fragments with minimal cohesion between them, the picture changes. A weak interior allows the tidal deformation to propagate more effectively. The body flexes more. The surface layer, which may be slightly more cohesive than the interior due to compaction of fine-grained regolith, experiences greater strain. And when that strain exceeds the tensile strength of the surface material, it cracks. The required surface strength is remarkably low. Herford's models showed that tensile failure of the surface layer could occur at stresses as low as roughly 1 kilopascal, comparable to the strength of compacted lunar regolith measured in laboratory experiments. This means Phobos does not need to be made of wet tissue paper for the grooves to form. It just needs to be what everything we know about it suggests it is: a porous, loosely bound body with a thin, somewhat cohesive outer layer draped over a structurally weak interior. Subsequent research has strengthened this interpretation. In 2022, a numerical simulation study by Chung and colleagues modeled the response of Phobos' surface to extensional fracturing caused by tidal forces. They showed that when fractures open in the cohesive surface layer, loose material from above drains into the cracks, producing the groove-like depressions observed on the surface. The model predicted groove geometries that matched many of the observed features at mid-latitudes, supporting the idea that the grooves are actively forming drainage channels above deep-seated tidal fractures. Not every groove fits the tidal model perfectly. There are areas on the surface, particularly on the leading hemisphere of the moon, where grooves are absent or oriented in directions that do not align with the predicted stress field. Some of these absences may reflect regional differences in surface properties, areas where the cohesive layer is too thin to record the strain, or where impact gardening has erased the evidence. Others may genuinely require alternative explanations, including the original Stickney impact hypothesis, or secondary processes such as ejecta scouring from nearby impacts. The picture is not perfectly clean, but the dominant pattern is clear. The majority of the grooves correlate with tidal stress, and the correlation grows stronger with every new analysis. It is worth walking across the surface of Phobos in more detail, because the geography of the grooves tells a richer story than any single summary can convey. The grooves are not a uniform population. Scientists who have mapped them in detail have identified several distinct families, each with its own orientation, width, depth, and spatial distribution. The families overlap in places, cross-cut each other in others, and collectively create a surface texture that is unique among all known bodies in the solar system. The most prominent family of grooves runs roughly parallel to the sub-Mars direction, converging symmetrically around the point on Phobos that perpetually faces the planet. These are the grooves most strongly associated with the tidal stress model. Their orientations align closely with the directions of maximum tensile stress, calculated by Herford and his colleagues. They are the cracks you would predict if the moon were being stretched along the Mars-facing axis, which is precisely what tidal forces do. A second family of grooves clusters around Stickney Crater. These are the features that initially led researchers to attribute all grooves to the impact event. They radiate outward from the crater rim in patterns consistent with fracture propagation from a point source. Some of these grooves are among the widest and deepest on the surface, reflecting the enormous energy released by the Stickney impact. These impact-related grooves are real and distinct from the tidal grooves, but they account for only a fraction of the total groove population. A third family appears on the leading hemisphere of Phobos, the side that faces forward in the direction of orbital motion. These grooves have orientations that do not fit cleanly into either the tidal stress model or the Stickney impact model. Their origin remains debated. Some researchers have proposed they may result from secondary impact processes, chains of craters created by debris striking the surface at shallow angles. Others have suggested they may reflect a different component of the tidal stress field that is not captured by the simplest elastic shell models. The leading hemisphere anomaly is one of the open questions that the MMX mission may help resolve. Beyond the grooves themselves, there is another surface feature that has drawn increasing attention in recent years. Certain regions of Phobos appear spectrally distinct from the rest of the surface. These areas, informally called the blue units because they appear slightly bluer in colour relative to the overall reddish-grey terrain, are found primarily in areas of steep topographic slope, inside crater walls, and along the edges of grooves. They are interpreted as exposures of fresher, less space-weathered material from beneath the surface. The leading explanation for how this material gets exposed connects directly to tidal forces. As Phobos orbits Mars, the tidal stress field is not constant. It oscillates with the moon's slightly eccentric orbit, producing a rhythmic flexing of the surface. This flexing drives what researchers call granular creep, a slow downslope movement of loose regolith under the influence of time-varying tidal and rotational forces. Over thousands of orbits, the creep gradually moves surface material downhill, exposing the less weathered subsurface material beneath. The blue units are essentially windows into Phobos's interior, opened by the same tidal forces that are carving the grooves and stealing the orbital energy. The surface of Phobos is not static. Material is migrating. Fresh surfaces are being revealed. The entire regolith layer is in a state of slow, continuous motion driven by the tidal environment. Phobos is not just cracking, it is shedding its skin. This has a profound implication. It means the grooves on Phobos are not ancient relics of a long-ago catastrophe. They are contemporary features. They are forming now in the present geological era as a direct consequence of the same tidal interaction that is pulling Phobos inward. The moon is not simply falling toward Mars. It is being deformed as it falls. The stresses are warping its shape, cracking its surface, and rearranging its internal structure in real time. And the deformation is not limited to fracturing. Research published by Shai and colleagues examined high-resolution images from the Mars Express orbiter and identified mass-wasting features inside craters on Phobos, landslides where material on crater walls had slumped or flowed downslope. When they modeled the dynamic slopes on the surface at different orbital distances from Mars, they found that the increase in slope caused by tidal forces correlated with the locations of observed landslides. Craters near the sub-Mars and anti-Mars points, where tidal effects are strongest, showed the most evidence of slope failure. This means the surface of Phobos is mobile. It is not a frozen landscape unchanged since the last major impact. Material is moving, regolith is shifting, crater walls are collapsing. The changing tidal environment, growing stronger as the orbit decays, is actively reshaping the topography of the moon. Phobos is not just cracking, it is eroding from within, rearranging itself under the influence of forces that grow a little stronger with every passing century. There is an additional clue that connects the surface to the interior in a way that deepens the sense of structural fragility. Phobos has a remarkably low bulk density, approximately 1.87 grams per cubic centimeter. This is significantly lower than the density of solid rock, even the relatively lightweight carbonaceous chondrite material that Phobos's surface chemistry resembles. The low density implies a high porosity, perhaps 25 to 35% by volume. Phobos is full of voids. Its interior is riddled with empty spaces, gaps between blocks, cavities left by incomplete compaction, perhaps even large internal voids where sections of rubble sit loosely against one another without mechanical bonding. A body with this much internal void space is structurally vulnerable in a way that a solid body of the same size would not be. It deforms more easily under tidal stress. It transmits forces differently. It responds to changing conditions not as a rigid object, but as something closer to a bag of gravel, capable of shifting, settling, and reorganizing internally under the right circumstances. The grooves on the surface may be only the most visible symptom of a much more pervasive structural rearrangement happening throughout the moon's volume. All of this leads to the central question: what happens when the orbit decays far enough that the tidal forces exceed the structural limits of this fragile, porous, already cracking body? There are two possible outcomes, and they are not equally likely. The first possibility is a direct collision. In this scenario, Phobos remains intact as it spirals inward and eventually enters the Martian atmosphere, where aerodynamic forces tear it apart and the fragments rain down onto the surface. This would be a spectacular event by any measure. The impact energy of a body the size of Phobos striking a planet at orbital velocity would be enormous, creating a crater hundreds of kilometers in diameter and ejecting vast quantities of material into the Martian atmosphere and beyond. But most researchers consider direct collision the less likely outcome. The reason comes back to the Roche limit and the structural weakness of the moon. Long before Phobos reaches the Martian atmosphere, it will cross the distance at which tidal forces exceed the cohesive and gravitational forces holding it together. For a body as weak and porous as Phobos appears to be, that distance is well above the Martian surface. The moon will be pulled apart before it gets close enough to hit the ground. The second possibility, and the one that most current models favor, is tidal disruption, followed by ring formation. In this scenario, as Phobos crosses the Roche limit, the tidal gradient overwhelms its internal structure. The moon does not explode. It does not shatter in a single violent moment. Instead, it begins to come apart gradually. Surface material sloughs off. Blocks separate along existing fracture lines. The body elongates, stretches, and eventually loses coherence as a single object, spreading into a stream of debris that continues to orbit Mars along the same approximate trajectory. Over time, that stream of debris spreads out. Collisions between fragments redistribute energy and angular momentum. The material organizes into a disk. Mars acquires a ring. This is not science fiction. It is a natural consequence of the physics involved, and it has been modeled in detail by multiple independent research groups. The pioneering work by Benjamin Black and Tushar Mittal, published in 2015, calculated the evolution of a debris ring formed from the tidal disruption of Phobos. Their simulations showed that the resulting ring would be relatively narrow and composed of particles ranging in size from dust to boulders, extending outward from the disruption zone in a disk roughly comparable in orbital radius to the current orbit of Phobos. The ring would not be permanent. Ring particles orbiting below the synchronous altitude would themselves be subject to the same tidal dynamics that destroyed Phobos. Over time, roughly 80% of the ring material would spiral inward and fall onto the Martian surface as a slow rain of debris. The remaining 20% could potentially reaccrete into one or more small moonlets, beginning a new cycle. What would that ring actually look like? The question seems almost fanciful, but researchers have modeled it in enough detail to offer a concrete picture. The ring would form close to Mars, occupying a narrow band roughly centered on the orbital altitude where Phobos disintegrated. Its radial extent would depend on how quickly the debris spread after the breakup, and how collisions between fragments redistributed energy and angular momentum. Initial models suggest the ring would span a few thousand kilometers in radial width, a thin band compared to the vast ring systems of Saturn, but substantial enough to be a prominent feature of the Martian system. The particles composing the ring would range in size from fine dust, micron-scale grains launched by collisions between larger fragments, to boulders and blocks several meters or even tens of meters across. The size distribution would evolve over time as collisions ground larger pieces into smaller ones, and as the smallest particles were gradually removed by radiation pressure and the subtle drag of Mars's tenuous upper atmosphere. From the surface of Mars, the ring would be visible to the naked eye. Its brightness would depend on the total mass of debris and the reflectivity of the particles. But given that Phobos contains a substantial volume of material, the ring would likely appear as a luminous arc stretching across the Martian sky, brightest when viewed edge-on near the horizon, and spreading into a broader band when viewed from latitudes where the ring appeared higher overhead. It would not rival Saturn's rings in grandeur. Saturn's ring system contains vastly more material and is spread across a much greater radial distance. But for a planet that today has no ring at all, the transformation would be profound. The Martian night sky would change from a canvas dominated by two small, fast-moving moons to a vista featuring a single small distant moon, Deimos, accompanied by a permanent streak of reflected light encircling the planet. The ring would not last. Models suggest that the majority of the ring material would rain down onto Mars within roughly 1 million to 10 million years, dragged inward by the same tidal mechanism that destroyed the moon. The infall would not be dramatic. It would be a persistent drizzle of small particles entering the atmosphere at orbital velocities, burning up high in the thin Martian air and settling as a fine layer of dust across the entire planetary surface. Over geological time, This deposited material would form a distinct sedimentary layer, a thin band in the Martian stratigraphic record marking the era when Mars consumed its moon. Some researchers have speculated that such layers may already exist. The Medusae Fossae Formation, a massive deposit of fine-grained, easily eroded material stretching across a region near the Martian equator, has been tentatively linked by some scientists to past ring infall events. The formation is one of the most enigmatic geological features on Mars. It stretches across an area roughly the size of Mexico. It is composed of material with an unusually low density, and its origin has never been satisfactorily explained by conventional volcanic or sedimentary processes. If earlier versions of Phobos were destroyed and formed rings that subsequently rained debris onto the equatorial region, the accumulated deposit could potentially account for some or all of the Medusae Fossae material. This hypothesis remains speculative and contested, but it illustrates how the destruction of moons is not an isolated orbital event. It is a geological process that leaves its fingerprints on the surface of the planet. This is precisely the scenario the Hesselbrock and Minton recycling hypothesis describes. Their 2017 model proposed that this cycle of moon destruction, ring formation, partial reaccretion, and renewed tidal decay has played out multiple times in Martian history. Each cycle produces a moon smaller than the last. Each moon spirals inward and is destroyed. Each ring rains material onto the planet and spawns a diminished successor. If this model is correct, Mars has had rings before, multiple times. Phobos is simply the current and possibly final iteration of a process that has been repeating for billions of years. The 2026 study in astronomy and astrophysics added important refinements to this picture. By modeling Phobos as a rubble-pile with realistic shape and varying cohesive strength, the researchers found that the disruption distance is likely farther from Mars than the classical Roche limit for a uniform fluid body. A weak, irregularly shaped rubble-pile begins to fail at roughly 2 to 2.2 Mars radii from the planet's center, compared to the rigid body estimate of roughly 1.6 Mars radii used in earlier studies. This larger disruption distance means the breakup would begin earlier in the orbital decay process and would produce a different distribution of debris sizes and orbital elements than models assuming the classical limit. The same study also noted that the shape of Phobos matters significantly. Its elongated triaxial form means that tidal stresses are distributed unevenly, with certain orientations producing failure at greater distances than others. The moon's specific geometry, the way its longest axis aligns with Mars, determines how it begins to come apart. The failure does not start uniformly. It starts at the point of greater structural vulnerability, likely along existing fracture networks, and propagates from there. There is something deeply unsettling about this picture. The grooves currently visible on the surface of Phobos may not just be evidence of tidal stress. They may be the predetermined fault lines along which the moon will eventually disintegrate. The fractures that tidal forces are carving today are the same fractures that will serve as the breaking points millions of years from now. Phobos is being pre-scored for its own destruction, like a sheet of glass with a line scratched across its surface. When the force comes, it will break along the line that was drawn long in advance. The upcoming MMX mission represents the best opportunity humanity has ever had to test these models against direct evidence. When the spacecraft lands on Phobos and collects samples, The physical properties of the surface material will be measured directly for the first time. Cohesive strength, grain size distribution, porosity, mineralogy, and internal structure can be constrained in ways that remote observation cannot achieve. The small French-German rover called Idefix will drive across the surface, testing how the regolith responds to mechanical contact in Phobos' near-zero gravity, providing ground truth for the models that predict how this material will behave under increasing tidal stress. Equally important, the gravity science conducted during MMX's orbital phase will map the internal mass distribution of Phobos, revealing whether the interior is uniformly porous or contains denser and less dense regions, voids, or structural boundaries. This information will directly determine where in the spectrum of disruption models Phobos falls and how close it already is to structural failure. These specific measurements MX will make deserve closer attention, because each one addresses a different facet of the question, and each one could shift the timeline in a different direction. The most critical unknown is cohesive strength. If the near-surface material of Phobos has a cohesive strength of only a few kilopascals, comparable to loosely compacted sand, the Moon will begin to structurally fail at a relatively large distance from Mars, well above the classical Roche limit. Disruption could begin within roughly 10 to 20 million years. If the cohesive strength turns out to be higher, in the range of tens or even hundreds of kilopascals, suggesting a surface cemented by impact processes or mineralogical bonding, the Moon could survive to a closer distance, pushing the disruption timeline further toward 50 million years or beyond. The difference between those two outcomes, separated by a factor of 3 or more in time, depends on a physical property that can only be definitively measured by touching the surface and testing the material. The coring sampler aboard MMX will penetrate to a depth of at least 2 centimeters below the surface, collecting material that has been shielded from space weathering and micrometeorite bombardment. The grain size distribution, mineralogy, and mechanical properties of this subsurface material will provide the first direct constraints on how tightly Phobos' outer layer is bound together. Meanwhile, the pneumatic sampler will collect surface-level regoliths for comparison, allowing scientists to assess how space weathering has altered the mechanical properties of the outermost layer. The Idefix rover adds another dimension. By driving across the surface on 4 wheels in gravity roughly 1/1800th of Earth's, the rover will observe in real time how the regolith responds to mechanical contact. Whether the surface compresses, fractures, or supports the wheels across a firm crust will correspond directly to the material properties that determine which disruption scenario applies. The gravity science campaign during the orbital phase will map Phobos' internal density distribution by tracking the spacecraft's trajectory as it flies close to the Moon. Variations in gravitational acceleration reveal where mass is concentrated and where voids may exist. If the interior is uniformly porous, the disruption models can assume a homogeneous rubble-pile. If there are denser cores surrounded by looser material, or large internal voids that create structural weak points, the models must account for a more complex failure geometry. The difference matters. A homogeneous rubble pile comes apart relatively uniformly, shedding material from all sides. A body with internal structure comes apart along boundaries between regions of different strength, potentially producing larger intact fragments that survive longer before being ground down by collisions within the resulting ring. Each of these measurements feeds into the same fundamental question: how strong is Phobos, and how much time does it have? The answer is encoded in the dust on its surface, the density variations within its interior, and the mechanical behavior of its regolith under the lightest possible touch. MMX is designed to extract that answer. And when it does, the timeline of Phobos's destruction will shift from a range of estimates spanning tens of millions of years to a much narrower window defined by direct physical evidence. We are living in the narrow window of time during which this question can be studied by visiting the object. Phobos will not survive indefinitely. In 10 million years, or 30 million, or 50 million, it will be gone. The moon that orbits Mars today, the one that future MMX samples will be extracted from, will no longer exist. It will have been converted into a ring of debris, a rain of fragments, or the seed material for a new, smaller, shorter-lived successor. The window during which Phobos can be studied as an intact body is finite, and on geological timescales, that window is already closing. Consider the strangeness of the current moment. Right now, at this instant, Phobos is orbiting Mars roughly 6,000 kilometers above the surface. Its grooves are visible. Its shape is intact. Its orbit, though decaying, is still well above the Roche limit. To any instrument, to any camera, to any spacecraft passing by, it looks like a moon. It behaves like a moon. It occupies the space in the Martian system where a moon belongs. But everything we know about the physics tells us this is temporary. The forces acting on it are measured. The trajectory is calculated. The structural vulnerabilities are mapped. The fracture lines are visible. The interior weakness is inferred from the density measurements and supported by every model of its formation and evolution. Phobos is intact today the way a sandcastle is intact before the tide comes in. The structure exists. The forces that will destroy it are already present. The only variable is time. And time, on a planetary scale, is not on Phobos' side. The evidence is carved into every groove on its surface. It is encoded in its density. It is written in the tracking data from every spacecraft that has measured its orbit. It is confirmed by the physics of tidal interaction that governs every moon, every planet, every orbiting body in the universe. Phobos is not simply a moon that will eventually be destroyed. It is a moon that is being destroyed right now, in the present tense, at a pace that is invisible to human perception but unmistakable to measurement. The grooves are getting wider. The orbit is getting lower. The stresses are getting stronger. And somewhere in the future, separated from us by a span of time that feels immense to a human being, but amounts to a rounding error in the age of the solar system, the last fragment of Phobos will either join a ring around Mars or fall onto the Martian surface as debris. When that happens, Mars will have consumed its closest companion. The moon named for terror will have been destroyed by the planet named for war. And the process that killed it will not have been violent in any way a person would recognize. It will have been gradual, patient, and quiet, written in fractures so shallow they could be mistaken for scratches, measured in an orbital decay so gentle it took spacecraft to detect. But the full weight of what is happening to Phobos only becomes clear when you stop looking at the mechanics and start looking at what they mean. We do not think of moons as temporary. That is the instinct we need to confront before we can understand what Phobos really is. When you look at the night sky and see the moon hanging above the horizon, you see something that feels eternal. It was there before you were born. It will be there after you die. Your grandparents saw the same moon. Their grandparents saw the same moon. Every generation of human beings that has ever lived looked up and saw the same pale disk crossing the same sky, and not one of them ever had reason to doubt that it would always be there. Moons feel like fixtures. They feel like architecture. They feel like permanent features of the planetary systems they inhabit, as reliable as the sunrise, as dependable as the ground beneath your feet. Phobos dismantles that assumption with the quiet efficiency of mathematics. Here is a moon that orbits its planet right now, today, at this moment. It crosses the Martian sky 3 times every sol. It has been doing so for millions of years. If you were standing on Mars this evening, you would see it rise in the west, drift overhead, and set in the east. And nothing about its appearance would suggest anything other than permanence. It looks like it belongs there. It moves like it has always been there. It behaves in every observable way like a moon that is doing what moons are supposed to do. But it is not permanent. It is not stable. It is not safe. It is falling. And it has been falling for longer than most of the complex life on Earth has existed. And it will continue to fall until there is nothing left of it to fall. The grooves on its surface are the slow-motion record of its disintegration. The orbital tracking data from decades of spacecraft measurements confirm that the distance between Phobos and Mars shrinks by a measurable amount every single year. The physics of tidal interaction guarantees that this process cannot be reversed, cannot be paused, and cannot be avoided. Phobos will be destroyed. The only question is the precise mechanism and timeline, and even those uncertainties are narrowing with every new study. This is what makes Phobos genuinely unsettling in a way that most space stories are not. It is not a tale of sudden catastrophe. There is no asteroid screaming toward a planet. There is no gamma-ray burst sterilizing a hemisphere. There is no supernova catching a solar system by surprise. The destruction of Phobos is happening in full view, in slow motion, with complete predictability, and there is nothing dramatic about the pace. 1.8 centimeters per year. That is the speed of doom. That is the velocity at which a moon dies. And that is precisely what makes it so disturbing. We are wired to fear sudden threats, an explosion, a collision, a flash of light. Our brains evolved to react to things that happen fast, because fast things are the ones that kill you before you can respond. Phobos offers the opposite, a threat so slow that no living creature will ever perceive it directly. A destruction so gradual that a million years of it would be invisible to the naked eye. And yet the outcome is exactly the same as if it happened in an instant. The moon is destroyed. The debris falls or spreads into a ring. The companion is lost. The sky changes forever. There is a concept in environmental scholarship called slow violence. It was originally applied to environmental destruction, the idea that some of the most devastating changes on Earth happen too gradually for people to register as crises. Coastlines erode over decades. Aquifers are draining over centuries. Species disappearing one population at a time across generations. The damage is real, the outcome is catastrophic, but the pace defeats human attention. We do not react to what we cannot perceive, even when the evidence tells us it is happening. Phobos is slow violence on a planetary scale. The forces are measured. The trajectory is calculated. The outcome is known. And the pace is so far below the threshold of human perception that it might as well be invisible. If Phobos were falling at a rate that would destroy it in 100 years, it would be the most urgent story in science. If it were falling at a rate that would destroy in 1,000 years, it would be a global concern. But because the timeline stretches across tens of millions of years, it registers as a curiosity. An interesting fact about Mars, a trivia question for astronomy enthusiasts. Something that will happen, yes, but so far in the future that it barely feels real, and yet the process does not care about human attention spans. It does not care that we cannot see it. It proceeds at exactly the same rate whether anyone is watching or not. Phobos was falling before the first human looked up at the stars. It will continue falling long after the last one does. Let us consider what Mars will look like after Phobos is gone. If the tidal disruption models are correct, and most current evidence suggests they are, the first visible change will not be the disappearance of Phobos, but its transformation. As the moon crosses the Roche limit and begins to lose structural integrity, it will elongate. Its shape, already irregular, will stretch along the tidal axis until the body can no longer maintain coherence. Fragments will separate. Blocks that were held in place by friction and minimal cohesion will drift apart. The moon will become a chain of debris, then a stream, then an arc, and finally a ring. Mars will have a ring. Not a ring like Saturn's, vast and luminous and visible across the solar system. The Phobos ring would be modest by comparison. A narrow band of rubble and dust orbiting close to the planet. Visible, perhaps, as a faint streak across the Martian sky for an observer on the surface. But it would be a ring. Mars, the dry red world with its thin atmosphere and its dead volcanoes and its frozen poles, would wear a crown of debris made from the body of its own destroyed moon. The ring would not last forever. Nothing about this system lasts forever. The same tidal forces that destroyed the moon would go to work on the ring. Particles below the synchronous orbit would gradually spiral inward, dragged by the same trailing bulge mechanism that killed Phobos. Over millions of years, the majority of the ring material would fall onto Mars, raining down as a thin but persistent dusting of debris across the Martian surface. Some fraction of the material would reaccrete into one or more small moonlets at the outer edge of the ring, where the dynamics favor aggregation over dispersal. Those moonlets would be tiny compared to Phobos, perhaps only a few kilometers across, and they too would begin their own inward spiral. The cycle would continue, diminishing with each iteration, each new moon smaller and shorter lived than the one before, until the remaining mass was too small to form a coherent body and the last traces of what was once Phobos settled onto the Martian surface as dust. The Hesselbrock and Minton model suggests this cycle may have already repeated 3 to 7 times over the history of Mars. Each generation of moon was smaller than the one before it, reduced by the fraction lost to ring material raining down onto the planet's surface. What began as a massive satellite born from a giant impact billions of years ago has been whittled down across successive cycles of destruction and reformation to the small, battered body we see today. The Martian surface may already contain the pulverized remains of all those earlier moons, mixed into the regolith, indistinguishable from ordinary soil, their existence recorded only in the sedimentary layering that future geologists might one day detect. This means the relationship between Mars and its inner moon has never been one of stability. It has always been one of consumption. Mars raises tides on its companion. Those tides steal energy. The companion falls. It breaks apart. Its remains fall onto the planet or briefly form a ring before following the same path down. Mars consumes its moons the way a slow fire consumes fuel, patiently, completely, leaving only ash. There is a broader lesson here that extends beyond the Mars system, and it concerns the nature of orbits themselves. We think of orbits as stable things. A planet orbits a star. A moon orbits a planet. The system persists. The motion continues. The relationship endures. And for many systems in the solar system, that intuition is roughly correct over human timescales. Earth's orbit around the Sun is stable for billions of years. Jupiter's major moons have been in their current configuration for most of the solar system's history. The architecture looks permanent, but permanence is an illusion of timescale. Every orbital system is governed by forces that are constantly transferring energy between the bodies involved. Tidal interactions, gravitational perturbations from other bodies, resonances that amplify or dampen orbital parameters over millions of years. All of these processes are always operating. In some systems, the forces are balanced in ways that produce genuine long-term stability. In others, the balance is temporary, and the system is slowly evolving toward a configuration that will look nothing like the current one. Phobos is simply the most visible and most dramatic example of an orbital system in active decay, but it is not the only one. Triton, the largest moon of Neptune, orbits in the retrograde direction opposite to Neptune's rotation. This means the tidal interaction is pulling Triton inward regardless of its orbital altitude. Like Phobos, Triton is falling. Unlike Phobos, Triton is much larger and much farther from its planet. So the timescale is longer, likely billions of years rather than tens of millions. But the outcome, eventual tidal disruption or collision, is the same in principle. Miranda, one of the inner moons of Uranus, tells a different version of the same story. Its surface is a fractured patchwork of geological provinces that do not match. Vast canyons cutting through terrain that looks as though it was shattered and reassembled. For decades, scientists believed Miranda had been physically broken apart by an ancient collision, and then gravitationally reaccreted into the jumbled world we see today. More recent analysis suggests that tidal heating, driven by a past orbital resonance with the other Uranian moons, may have driven the violent geological activity that scarred its surface. The resonance has since faded. The heating has stopped. Miranda survives, but it carries the marks of a tidal history that came close to tearing it apart. It is a moon that endured what Phobos will not. Even Earth's moon, the one we look at every night and consider permanent, is not truly fixed in place. It is drifting outward, widening the distance between itself and the planet it orbits, year by year, century by century. In the very distant future, billions of years from now, when the Sun has expanded into a red giant and the Earth-Moon system faces the end of its existence, that slow widening will have reshaped the relationship between the two bodies in ways that would be unrecognizable to anyone alive today. Our moon is moving toward a future in which it is farther, smaller in the sky, and weaker in its influence on the tides. Phobos is moving toward a future in which it no longer exists. Two moons, two trajectories, two endings, both written by the same force that neither moon chose and neither moon can refuse. This is perhaps the deepest lesson Phobos has to teach. Companionship in the orbital sense is not a permanent state. It is a negotiation, a constant exchange of energy between two bodies linked by gravity, mediated by the deformation of their interiors, governed by the geometry of their orbits. Some negotiations produce stability, others produce drift, and others produce destruction. The outcome depends not on any quality of the moon itself, not on its size or its beauty or its significance, but on where it happens to be relative to a single invisible line in space. Above the synchronous orbit, a moon gains energy and retreats. Below it, a moon loses energy and falls. The line doesn't care. The physics does not care. The planet does not choose to destroy its moon. It simply deforms under the tidal stress, and the lag in that deformation creates a force, and the force does what forces do. Phobos was born or reformed or captured into an orbit below that line, and from the moment it arrived there, its fate was determined. Not by a decision, not by a catastrophe, not by anything that could be called an event, by geometry, by the simple fact of being in the wrong place. That is the terror of Phobos. Not that it will be destroyed by some exotic force or unprecedented disaster. Not that it faces a threat from outside the system, some rogue body or cosmic accident. The threat is the system itself. The same gravity that holds Phobos in orbit is the gravity that will tear it apart. The same relationship that makes it a moon is the relationship that is killing it. There is no external villain in this story. There is only the quiet, mechanical, implacable operation of forces that were set in motion long before anything alive existed to witness them. And there is no rescue. No intervention can save Phobos. Even if a civilization existed on Mars with the technology to attempt it, the energy required to lift Phobos above the synchronous orbit and into a stable, outward migrating trajectory would be staggering beyond comprehension. The moon is trapped on the wrong side of a gravitational boundary, and the cost of crossing that boundary increases with every year as the orbit decays further. Phobos is not in danger the way a person standing near a cliff is in danger, where a single step backward would bring safety. It is in danger the way a river is in danger of reaching the sea. The current flows in one direction. The gradient allows no reversal. The endpoint is defined by the landscape itself. Right now, in this year, in this moment, a spacecraft sits on a launch pad in Japan, preparing to travel to this doomed world. The MMX mission will arrive at Mars, orbit Phobos, deploy a rover onto its surface, collect samples of its dust and rock, and carry them back to Earth. Scientists will open sealed containers in clean rooms and examine material from the surface of a moon that is in the process of being unmade. They will measure its composition. They will analyze its structure. They will determine its origin and constrain the timeline of its destruction. They will hold in their hands fragments of a body that will not exist in its current form for much longer. On the timescale of the solar system, those samples will be among the most remarkable objects ever brought to Earth. Not because of their material value, not because of their rarity in a chemical sense, but because of what they represent. Evidence collected from a world that is already dying. A geological snapshot taken during the slow unraveling of a moon. A record of a body caught between existence and oblivion, still intact, still orbiting, still crossing the Martian sky 3 times every sol, but moving inexorably toward its own end. Phobos does not know any of this. It is a rock. It has no awareness, no experience, no capacity to comprehend its own trajectory. The name it carries, fear, was given by human beings projecting human meaning onto an indifferent universe. The grooves on its surface do not mean anything to Phobos. The orbital decay does not register as loss. The approaching Roche limit is not a deadline in any conscious sense, But we know. We are the ones who measured the decay rate. We are the ones who mapped the grooves and connected them to tidal stress. We are the ones who built the models that predict the ring, the rain of debris, the quiet disappearance of a companion that Mars never chose and cannot keep. We are the species that names things after fear and then calculates, with extraordinary precision, the schedule of their destruction. And what the calculation shows is this: Phobos is not a moon in the way we usually use the word. It is not a permanent companion. It is not a stable partner in the Martian system. It is a temporary structure, an object passing through a particular configuration of gravity and geometry that allows it to exist as a coherent body for a geologically brief period before the same forces that hold it in orbit pull it apart. It is a moon on borrowed time, and the loan is not renewable. When it is gone, Mars will be a planet with one moon instead of two. Deimos, the smaller, more distant, safer sibling, will continue its slow outward drift, gradually receding from Mars over billions of years. Mars will keep spinning, the sun will keep burning. The solar system will continue its patient evolution toward configurations that no living being will witness. And somewhere in the Martian regolith, mixed with the iron oxide dust that gives the planet its color, there will be grains of material that once belonged to a moon. Fragments so fine and so thoroughly blended with the Martian soil that no instrument could distinguish them from the native rock. The last physical trace of a world that once crossed the Martian sky 3 times a day, that rose in the west and set in the east, that was named after the god of fear, and that fell centimeter by centimeter, orbit by orbit, into the arms of the planet that created it, or captured it, or inherited it from the wreckage of a predecessor that fell the same way. Phobos is terrifying. Not because it is large, not because it threatens Earth, not because its destruction will happen in any time frame that matters to a single human life. It is terrifying because it demonstrates something that the universe rarely makes so visible. That destruction does not require violence. That doom does not require speed. That the difference between a moon and a memory can be nothing more than time and a centimeter per year. The fall has been underway for millions of years. It will continue for millions more. And the sky above Mars, where Phobos races from west to east 3 times every day, will grow imperceptibly darker each century as the moon sinks lower and lower and lower, until the night it does not rise at all,